testing it. Yeah, you are the chair, so to say. No. Hi, morning, everyone. Welcome. Good morning on a very rainy morning in Warsaw. Welcome to our presentation of the Bioculture FDT, which is one of ESA's FDT projects in terms of its new strategic direction up until 2040. There's been a group of us working on this. We're presenting on behalf of a larger team. And just to introduce the context from why ESA initially commissioned this FDT, one of many, I'll hand over to Ines. It's on, yes.
Hi, okay. So, good morning, everyone. My name is Inês Antunes. I'm from the European Space Agency. I'm a science coordinator in the Human Research Point of Contact in HRE. And today I come to talk or introduce or start the presentation together with my colleagues, our scientists fellows, to present you a tool that we have started defining a few months ago. It started initially, the name was a bioculture facility, but as we discussed, the title or the name evolved to become a space research and medical tool. And we kind of gave it the name of Asclepius. For the ones that don't know, Asclepius is a Greek figure from mythology and is associated with medical and care and medicine and healing. So, and it's exactly what the tool foresees. So it's just the right title. Because the concept will require, like, there is a lot of explanation about what it is, we have decided to split the presentation in two parts, one that will explain the concept and also get from you as a community feedback on things that you think we should consider. And then we will speak about how we foresee its implementation or development and deployment, because it will require some thought on how best strategically do it. So I will go also that we'll have questions and answers also with you, so you will also be asked. It's not only the other way around. So yes, so let's start it. Oops, going the wrong way. So before I start explaining a bit or introducing a bit the concept of this tool, I cannot do it without acknowledging and thanking the work of a huge team, really, that we worked with, and it was a great pleasure, at least for me, to work with them because they are incredible scientists and really good and nice experts and good people that I really had the pleasure to work with. So the tool, the activity was coordinated by me and Christian Hahn. Christian could not be here today, unfortunately. I don't know if you met her the other days, but she had to leave. So I will be representing ESA on her behalf as well, and presenting her part as well. And then also we got the support from our development and integration colleagues, Volker, Jutta, and Christopher. But I want to highlight really is the work performed by the scientists and experts that we worked with during the last months. We have, starting from the left to the right, top to bottom, we have Bjorn, Anne, Daniele, Alex that is here with us, Michael, Stefania, James, and Matteo, who are here with us, and then Loni, Theodore, and Roni. So all these scientists, they have different expertises, and they really added an incredible and critical input to the concept of this tool, and that's what we will speak with you today. So just to explain a bit why ESA wanted to, or decided that it was needed to develop such a tool and define a concept to develop such a tool. As we move to the Moon and Mars, we know that we will need tools and capabilities to really address the need to perform discovery science or bottom-up science, as you heard the concepts multiple times here, but also exploration-focused research and crew health science. We need to address those as we move to the Moon and Mars, and we need capabilities that really address, allow us to do that science, even though we will have challenges that are associated with those destinations. And also we need to develop a tool that is kind of, like a health support system for medical operations, where we will be able to, in flight, on real time, provide diagnostic capabilities as well as treatments as they are needed. And of course, if we develop such a tool, of course, it has a huge impact and application on Earth as well, especially on critical healthcare, where remote environments and hostile environments will definitely benefit for such a tool, where a hospital or a medical doctor is not nearby. So it really has a lot of interest and importance. But what are the challenges that I'm talking about that really made us decide to really develop such a tool, or think about such a tool, not develop, but to decide to define such a tool that needs development. Let's say that LEO, the low Earth orbit, it's a very comfortable environment in terms of we can resupply, we can bring down samples for return. If something happens, we can return the astronaut. There is good communications with ground. There is the crew is there exactly to work for science, so we have the crew available for us. So there are not much challenges that really affect medical operations and research. We can still perform a lot of things in LEO, but as we move to the Moon, as we move to Mars, the resupply will be limited. Downloading things, if we go to Mars, we cannot download. Communication, even Maybrit, I don't know if you met her, she's a flight surgeon, and she presented a very good presentation yesterday, and she was saying that just to send a message while you are in Mars transit to ground on Earth, it takes like one way 45 minutes, so you cannot communicate with ground on an emergency or on performing activities that require ground support. So we really have to address these challenges. Also the crew, like we will develop countermeasures to really protect crew performance, but also the crew, they will be also affected by spaceflight conditions. So they need to rely on tools that support their mission, the complexity of their mission, because the missions will be super complex as we move to Mars. So we have to address these challenges, and we need a tool, that's for sure. We need something that really supports science and medical operations on the crew health. So it needs to be independent, automated, versatile, flexible. So it really needs we will need it. So I will not go into detail. James, Alex, Matteo, they will go into detail, but to have such a tool, we have to consider sample preparation in cell cultures, in situ analysis, diagnosis, formulation or recycling, code storage, automation, artificial intelligence, and I put the 3 dots because we don't know everything. And we rely also today on you to tell us maybe if we missed something, if there is something that we should consider. So that's why I've put the 3 dots, because also this will be a very interactive session, I hope, where maybe you will also tell us, oh, by the way, did you think of this or did you think of that? And it would be good also to get that feedback from you. So that in the end, if we can define a tool, we reach a fully equipped and autonomous laboratory that really supports medical operations and really supports research. And now I give my words to Alex, right, Alex? Yeah, you have.
Thank you very much, Ines. Good morning. Dzień dobry, what I learned again. I tried to spell it, pronounce it right, I forgot yesterday. Yes, so as kindly introduced already by Ines, so what are the rationales? I mean, the 2 pillars are very clear. Yeah, it's the health monitoring, the health maintenance, therapies, and of course everything that is related to a crewed mission and its success. On the other hand, we have the other pillar that ESA has repeatedly announced with a good reason. Of course, we have to do research as well. So the two pillars of space, so research enabling space missions, manned or crewed space missions, and the research that derives from space itself. Yeah? So for us, it was very clear that these two elements play a very big role. And you can see here already the two headlines, so to say, why we do that is, of course, for crew health. So the monitoring, this is a big issue for, of course, the reasons that we discussed also yesterday and mentioned by Maybrit. So the crew needs to be monitored for their health status, as well as to verify and to modify probably the countermeasures at the right step. Prevention measures, diagnostics of a disease or the monitoring of a disease case. The therapy, this is something might be, when we move beyond the Earth vicinity, might become more interesting, that we cannot resupply any drugs or something, maybe even need to produce. And of course, together with all this, it comes that it has to fit to the individual needs. So from its, first of all, to identify in which stage of disease he is, on the other hand, how he can best be treated, depending on his individual case and individual disease state. On the other hand, this automation translations play a big role as well as for the research part. So what I mentioned before, the discovery research, I would say it's still targeted, not blue sky research, but it's really in space because it can be done only in space. But there are a lot of tools that we can take advantage of in space and microgravity for everything, like fundamental research, of course, in the microgravity environment, but as well, these are also tools which need to work in these environments to help, of course, due to research, to find the right tools and measures to support the crew health, and what has been listed here by us on the left side. So we have to do tissue repair probably, and when we go further, frostbite seems to be one of the issues that the MedOps has identified. We talked about the dust yesterday, which is a real issue as well. So all this, it's interlinked, so we can't believe that this is to be seen separately. Yeah? One important element, and when you see further the slides, you may see, wow, they are probably dreaming. No, or ESA is dreaming, and the scientists, we have to dream a little bit to achieve new goals, but nonetheless, it's very clear that this is a gradual development over time, because the complexity will increase the more we leave, Earth vicinity and the moon orbit. So where and when, of course, as mentioned by Ines before, Leo, everything might be quite easy. It's a comfort zone, so to say. And then this transitions to Leo moon, transitions more further to Mars, the flight there and the life on the planet then is adding a lot of more complexity, and it needs much more of these tools where you can really live there. Maybe, treat patients which have developed a disease where we have no drugs on board or on the spot, and that needs to be developed and synthesized on the spot. The next is exactly, and this is probably the introduction to the elements that will be shown further on. We'll not go too much detail here, but these are the modules that we thought are important to be developed. Also, step by step, not at once. Yeah? Everything has to be seen very carefully, depending on the destination and the needs, and also the developments here on Earth. I mean, we are progressing every year. There's always something new, so we cannot make a plan for 20 years or 30 how and what will be done and what will be available in 30, 20 years from now. So these are the analytics modules. So everything that has to do with, as you can see, imaging, screening, diagnostic, analytics module might be probably more important from the very beginning to the end. So it's a kind of module that needs to be developed earlier than later, probably. Then the sample preparation, maintenance modules, cell culture modules, very research, but also linked to the medical questions that may be raised, and the operational modules, as Ines also mentioned, we have limited download capabilities, the far we go, and they need cold storage, of course, for the upload and storage as well, recycling model synthesis, automation, and AI would play a bigger role the more we are independent from control from Earth, and this is something that it's a guiding line a little bit for the development of these modules. I think that we hope to discuss with you today, and this is the overall layout of a long discussion in the team. And I would probably hand over to you again, or One more, sorry, yeah. Wait a second. Ah, yes, I forgot about that one. And yeah, this is something very important. I think this is nowadays more than ever important to see what it is for and why we do that. Yeah? And of course, yeah, you can say there are health benefits for the crew. Obviously, this is the goal. But it's, oh, sorry. And sorry, I have to go back. Wait a second. I don't want to spoil that, yeah. But it has to be, it will lead to a lot of new it will be a technological pull and push in both ways. It will help us also to cope with, you know, health issues or treatment or life in extreme worlds. And unfortunately, the Earth itself becomes more and more an extreme world, so everything will be shifted. And of course, this is something we need to take into account, that we have to involve and include new stakeholders, and a big role maybe also of this concept. And this is probably, and we hope indeed that it could be inspiring also for young generations, for not only for the one or the other in the one or the other field. No, we have to think really in a very cross-disciplinary way. And this is something that has been very clear. Our team was so diverse in expertise, and I think this is the strength also of this endeavor, whatever it will be at the end. Yeah? But already the way to get there is a hopefully very enriching one, and will deliver a lot of spin-offs. And let's see how far we can get with that concept. And with the help of you and the community, we may polish, shape, reshape, and see how the stakeholders will buy in, and which element, and so on and so forth. So let's see how the discussion goes today, but I think this is it for now. Thank you.
Thanks, Alex. Yeah, so as Alex has very nicely just described there, when we first assembled as a team, in I think March this year. We've done a lot since March this year. Understanding what the remit for the FDT actually was, how we defined the facility, took a whole load of discussion. And as Alex has mentioned in a really great summary, there are these two key pillars. So we have supporting human health, particularly for increasing mission durations and complexity, but also for understanding the fundamental science that's going to get people to far destinations and also drive scientific discovery along the way. So the first thing that we defined really was the set of goals. So the toolkit, and as Alex has described, we've envisaged this as a toolkit of different components, different modules, different instruments, all working harmoniously towards particular goals, designed to support these two twin interlinked pillars. For enhanced crew health monitoring, particularly as we go into further destinations with greater reliance and autonomy. Automated healthcare management as well, so not just monitoring, but also the ability to reactively respond to crew health emergencies and changing health scenarios, even simply declining physiological performance. And development of countermeasures, which become increasingly relevant as durations become extended, and the requirements of countermeasures against extended spaceflight become more critical. But there's also a whole load of really interesting scientific discovery that we need to do to support these objectives and to support the remit of scientific discovery that has reciprocal benefits for Earth. So human cell adaptation, how do human cells across the different systems in our body respond to extended spaceflight? What are the basic conditions for life that we can discover from this unique laboratory in space and microgravity, particularly as we go beyond low Earth orbit? And identifying new hazards, so the unknown unknowns, as we sometimes call them, that we can't really even guess at yet in terms of what the effects of prolonged galactic radiation, for example, or very extended durations of microgravity, or changing gravitational vectors, or even living on Mars or the Moon and those different gravitational fields may have. So identifying all of these different things all work harmoniously in terms of setting our particular goals. One thing that really came out in all of our discussions as part of the FDT over the last 6, 7, 8, 9 months has been, although what we're proposing sometimes may seem ambitious, a lot of what we're proposing actually can already be accomplished on Earth. But to accomplish this in a unique vehicle in space and low Earth orbit or beyond, we're going to have to innovate. And we've identified some particular key areas for innovation. Automation, so particularly as crew performance may diminish, and as the sheer burden of doing a large number of experiments and medical monitoring increases, everything is going to have increasing levels of automation. I think anyone who's working in life sciences in the room will probably realize that automation of a lot of biological processes has been a real standout success over the last few years in terms of increasing amount of automation in all of our laboratory facilities to enable research. AI also is a very big area, so AI for both understanding the complex data and the large data sets that we're now generating, but also managing the complexities of experiments, both the experiments that are themselves individually complex and also have to occur in parallel. Interoperability, if we want this to be automated and controlled by AI, then there's going to be very limited opportunities for human intervention carrying samples between modules. So we have to have a lot of universality in terms of how the toolkit operates within itself. A lot of things have to be miniaturized. As I said, a lot of the stuff we're proposing already exists on Earth, but within a huge building. So a lot of the facilities are going to have to be miniaturized, and the essentiality of their function will have to be converted for performance on a vehicle. Inesh described that this is at least a 20-year timeline, so everything's going to have to be upgradable. As new technologies become improved and come online, we're going to have to be able to modularly change, adapt, edit, and improve the capabilities of the toolkit. And one area that I'm particularly interested in is sustainability and efficiency. To be able to get the most amount of performance over very long mission durations, everything's going to have to be far more sustainable and efficient. So closed-loop water recycling, reusable plasticware. We can't throw things away and get new things because on missions to Mars, we simply won't have that upload capability or the ability to carry that much mass. So to get into the toolkit itself, I think Alex and Inesh have both described quite nicely that we separated this into specific components, which all do core elements of what we want the overall toolkit to achieve. Such a toolkit doesn't exist, so we need to develop it. And as we develop this as the FDT, we were able to separate this into three distinct groups. So we have operational modules, so kind of the support modules, including a very evolved version of Melfi, so temperature-controlled storage for uploading the reagents, the samples that we need for the entire mission, even if it's a mission to Mars. And also for being able to store samples and bring them back to Earth, so download eventually. Formulation and recycling is going to be extremely critical, as I just mentioned, to make this an efficient working module over the entire mission duration, AI data analysis, and automation interoperability. We also have experimentation modules. So preparation module, which is kind of like, you can think of it as our clinical science facility, how it's going to take samples from crew, process them for further analysis, either cell culture or direct imaging and analytical and molecular analysis. Cell culture, so how we can proliferate, expand, and do cell culture experiments almost as a liquid handling profile platform on the ISS or on whatever vehicle this goes onto. And since most advances in cell culture and understanding life sciences are now happening through organoids, 3D tissue culture, and organoids and organs on chips, it's essential that we have the capability for doing 3D cell cultures as well. The analysis is actually fairly straightforward. So we split this into two modalities: imaging, particularly if it's functional imaging, and molecular analysis, so the two kind of standard readouts that we get mainly from our experiments. And as you probably realized, this isn't complete. We've identified the requirement for supplementary modules, which we aren't going to talk about in this presentation. We don't say that they're lacking. We think they're things that we can add to the toolkit to enhance its functionality, particularly a 3D bioprinter, so 3D biofabrication, which is another project that ESA is currently working on. The necessity for microbiology, which is going to be very relevant in a lot of these environments, but anyone who works in mammalian or human cell culture realizes you don't want to have microbes anywhere near your actual precious human cells. And also medical tools to really enforce that link with MedOps. One thing that I found, particularly in discussions with the group, was that sometimes this was quite hard to conceptualize as simply a whole load of paragraphs and as just a toolkit. So we created an artist's impression of how this toolkit could potentially look like. So I want to stress this is not how we are planning to build it, if any engineers are in the room. This is really just to help visualize the concepts of how these different modules, these different components of the toolkit could potentially interact together. So the operational modules, as I mentioned, there were 4. We have temperature-controlled storage, a very advanced version of Multi. Synthesis and recycling to take care of all the actual media formulations, creating RNA and creating primers, for example, as we need them from basic components, and then the AI and the automation. Essential features which we've now put into the CSR to take this forward for the temperature-controlled storage module is that it should be a universal sample storage and retrieval system, so it can be operated by automation and by AI. You need to have versatile size and configuration so that these modules can be capable of storing anything that we really want to, both upload and download. And complementation so that we can control the cryogenic temperatures throughout. For the synthesis and recycling module, again, there's this element of uniformity, so uniform interfaces to allow all of these processes to be automated, kind of as a liquid handling system. We need efficiency in economical water reclamation, particularly from cell culture waste, so that we're not just using multiple liters of cell culture media and then disposing of it. We can recover the vast majority of the upload mass, which is water from that, and use things like powdered media and formulation to make this much more sustainable. Manufacturing and synthesis of simple biomolecules, so all the molecules you might want to develop for interventions and also for molecular analysis tools. Waste processing concentration, again, to drive this forward towards the most efficient platform that's possible. And the isolation of cytotoxic and hazardous waste, particularly for things like imaging and molecular analysis, which we don't want to go back into the system. So a whole load of filtration to happen there. The AI and data analytics, this is a very black box at the moment. It's like HAL 2000. So we need powerful AI capability for automated experimentation. Huge amount of data storage. These are going to be very large data sets, and we won't always have bandwidth to download this back to Earth. Automated robotic operation in concert with human operation is going to be important, so we're going to have the ability for both. And a simplified user interface so that crew in whatever stage of capability they find themselves in over these mission durations are able to perform their experiments and also understand the data from these complex data sets. The experimentation modules, I think, are possibly the most exciting part, where we can do a lot of innovation. So we have a preparation module for taking crew samples. We have a cell culture module for performing basic cell culture proliferation and fundamental cell culture experiments. And then a 3D tissue engineering module, tissue culture module for more advanced 3D work. Essential features of the preparation module, again, we have automated robotic control and sample transfer between the modules, so we can transfer all the outputs from this preparation module of crew samples and also uploaded cryogenically preserved samples and material to other modules, so onwards to cell culture and then onwards to 3D tissue culture and to the imaging and analytical modules. Sample retrieval, as I say, manual intervention from the crew, so the ability for the crew to perform operations in person. Universal biosampling, so cell cryopods, all the things we normally introduce to take samples from the crew, biopsies, fluids, saliva, blood, for example. And integrated internal microfluidics, so that we can, again, use the massive advantages in bioprocessing and liquid handling systems that we now have across particularly biopharma labs, to transfer all of these samples to the appropriate analytical and processing stages. For cell culture, again, there's a variety of cell culture modalities and mechanisms that we can exploit, so things like hollow fiber bioreactors are very commonly used by NASA for proliferating cells and developing cell therapies as prototypes on the ISS. Something possibly like cubic, so we can incorporate universal biosampling. So if anyone who's done experiments on cubic, this is kind of like where cubic could plug into, so similar sort of cassettes for running organs on chip. And then the 3D tissue culture modality takes this one stage further by giving us the option to culture cells not just in simple micromass organoids and as monolayers or whatever format they are in microgravity, but all the way through to more complex organoids. And I'm giving a presentation this afternoon where I'm going to talk about some of the modalities that we can use for 3D tissue culture in the 3D tissue culture session, along with a few other colleagues. And again, essential elements of automated robotic operation and universal sampling and universal transfer. So conserving the type of format that each module passes onto the subsequent module. Finally, these aren't defined yet, and this is an area I think where we have the biggest need for input from the scientific community. Obviously, we're going to have to image all of these different experimental platforms, and we're going to have to do some complex molecular analysis, and particularly the type of molecular analysis and imaging that we think will be possible in 10, 15, even 20 years. What are these? We asked people, and basically they specify an entire imaging facility or a molecular biology floor of a hospital, which is going to be a very impractical way of transporting that much mass. So we have to think really carefully about what the essentialities of both imaging and molecular analysis as we progress through the strategic deployment plan actually are. What do we need? What's the minimum we need? And how can we make that minimum most effective? I've also put a QR code in here. You can actually, if you want to, download and play with this model. It's fully interactive. You can look at individual modules by themselves rotated around. And we hope to continue to develop this and add more essential features to it. So this will continue being live for the duration of the FDT development, which is going to be over the next few months up to the next year, we suppose. So as we incorporate new elements into this basic cartoon explanation, if you want to play around with it, feel free to just go to that QR code and you can download it and play with it as much as you wish. One of the things that we did probably about halfway through developing the FDT as part of our team was we realized that we kind of have to test how we're developing this with particular usage cases. Envisage a scenario which we think is likely from either of those two pillars, either medical support or fundamental research. And how can we actually deliver that using the toolkit? Can we test the toolkit with particular scenarios? So Alex, I think over to you to describe the first one from a medical perspective, if you want to present this. There's a lot of text on this slide, which you don't have to read. It's really all about how each of these individual modules has a particular role in solving this objective.
Thank you, James. To be honest, I like the model even better when it's on the big screen. It's really fantastic. Yes, I mean, the usage cases are also related to the mission design, probably the duration of the mission, and it starts probably with a simple question, you know, how to deal and how to identify when you are on the mission to Moon or Mars, how to identify a very simple disease case. You have fever, probably an infection of unknown origin, yeah. Somebody gets sick on board, very simple, yeah. That happens here on Earth quite often. And the question is, especially based on the knowledge that we have gained in the past 20, 30 years on crew exposed to this exposome of space with all the hazards and myriads of influential factors, stressors that are affecting the immune system. So it's getting sick, yes, the one thing, getting sick in space is another thing for the reasons and also for the way how you can diagnose and treat it at the very end. So as mentioned here, you know, they're more vulnerable to viral reactivations, impaired wound healing can be an issue. This is maybe also for other use cases interesting when it comes to frostbites, etc. And they all lead to an imbalanced immune system and to a risk of disease under these conditions, as I mentioned, with the radiation exposure and all the other factors. So the objectives of these usage cases, you know, like a patient who go to this practitioner, yeah, with fever and likely an infection, to identify, you know, is it really an infection, what it is about, which stage it is. So biomarkers which are associated with fever and infection, and this could be done through tools that are used here on Earth, but maybe even more profound when we develop our technologies here further. The question is, are the pathogens present, and what can we learn about that? Is an easy drug available for that or not? Of course, we need to understand, you know, how the interaction between this the germ and the dysregulated immune system is working towards these radiation confinement microgravity environments. And of course, when this is happening more frequently, or when a real cause is to be identified to be more frequent, you know, focused diagnostic assays can be or shall be developed, and a line of actions behind that to enable really to discover this ahead when it may, you know, blow up as an infection or as a disease. You know, when you can understand the disease cases better, you can diagnose them earlier and prevent from further disease progress. And these strategies are, of course, including at the very end to have the best possible pharmaceutical intervention in the treatment of this individual, and of course to complement it with other countermeasures or complementary measures like nutritional, behavioral, and other therapies in respect of a holistic view that we discussed yesterday, or was it before yesterday already? Yeah, oh, yesterday. And yes, to have this picture of the whole crew member exposed to this environment. And here are, so to say, the modules that James has presented and their interaction with these questions or this use case, you know. Of course, you need, I will go through it quite quickly, but you can imagine, you know, you need to store the material, you need to upload it probably before. And also you need, when it's a very disease case that you have probably not discovered before, something new and that you cannot really scale where it is and what it is, you have to probably store these samples for a longer time to bring it back to Earth, according to the mission duration. Dependently, we'll see how much space is there. Of course, when something new develops, so to say, or when you reach your limits with the material that you have uploaded, of course, you need to synthesize new proteins, new antibodies, and device to also to diagnose and probably also to treat the germ that you have identified. AI data analysis, we are aware of that already today. I mean, certainly many of you have been working with big data already in medicine with the omics. This is already a term which covers more or less many fields that are difficult to integrate and to understand, and that we are getting also to our limits here. And we need appropriate data analysis here to also to understand the data that we can generate on the spot with the PCR analysis, nanopore, microfluidic assays, and so on, to understand the whole suite of data in a better way. Yes, at the end, yeah, the crew time is important, and reliability of the analysis is as important, especially when you have limited resources. So the automation and interoperability is playing a big role to have a good data set to work with. Yeah. Of course, the sample type can be manifold. There can be blood, saliva, wound swabs, for instance. When you have a skin infection, it could be also viral skin infection. And you have to prepare the sample in the best possible way, depending on the sample type. You know, either it's only liquid, or there are cells or bacteria, and to be investigated and to understand, you know, in the best possible way what this biospecimen is delivering you. Of course, and we know this also from Earth, you need to understand, you cultivate the cells. For instance, some questions can only be answered when you challenge your system, so we challenge the immune system to get an answer. Like an intelligence test, you have to ask questions to get the right answer. So you have to have culture systems, as James pointed out. So they are interlinked. It's not another silo. Oh, this is the cell culture. This is something for biologists. No, this is working really interconnectedly. Yeah, and you know, 3-tissue cultures, this is the next step here on Earth. This can be also very helpful and in space as well. Yeah, and of course, yeah, the old microscope, so to say, for visualizing is probably not an old microscope anymore, but the real advanced imaging procedures with appropriate dyes and stainings and so on to identify what you anticipate to in this case. And of course, molecular analysis, which are of course interconnected to the step above cell culture and 3D culture technologies. So all needs to be embedded into one big picture. And you may see here just a very simple case. Yeah, patient comes to the doctor, so to say, with fever and infection, but in space, there are a lot of more steps to consider, because you have only limited resources, and you cannot ask or send the samples to somewhere because you are somewhere. Yeah, so this is the challenge in this easy use case even, and more use cases to come. Thank you.
Thanks, Alex. Yeah, so we have this and another usage case just to briefly discuss. Again, a lot of text, which you don't necessarily have to read, but one of the example use cases was to understand the change in function of particular organoids. There's been some really great talks over the last couple of days on the unknown but predicted effects of galactic radiation as we go beyond low Earth orbit, we're going to experience this a lot more, or at least the crew are. And so understanding particularly how particular organ systems, particularly really critical organ systems, are impacted by increasing mission durations and exposure to things like galactic radiation affect those systems. So one thing that would be useful for the crew is to have a surrogate measurement, so their own organoids being cultured in real time on the vehicle alongside them as they perform the mission, so that we can interrogate those, for example, kidney organoids, many organoids as well, to really understand what the mechanisms of that dysregulation caused by these conditions are, and develop countermeasures that are effective to them. It's no good to wait until the crew members become severely debilitated with low kidney function. Understanding what those mechanisms might be and how to counteract them is going to be really, really important. One final user case, and I can present this matter if you like, is really just in terms of the, thanks Matteo, really is looking at the 3D tissue culture. So Matteo and I both work in regenerative medicine, in tissue engineering, and particularly interested in what the potential for taking tissue engineering into space might be to solve a lot of the problems that tissue engineering was initially established to resolve on Earth. As Alex mentioned, ESA MEDOPS have really identified the risk of burns, particularly cryogenic burns on long mission durations, being difficult to treat and likely to involve infection and also result in very poor healing by themselves. So although this is one of our more ambitious user cases for missions to Mars, where we don't have ability to return crew members in these eventualities, and these become mission critical and potentially life critical to the actual crew member, developing capability for having applied tissue engineering and applied regenerative medicine on these vehicles is going to be really important. So we have a few other user cases in our CSR which become increasingly ambitious, involving things like CAR T-cell therapies for treating leukemias induced by galactic radiation, which we aren't going to cover now. But we're really thinking about how we can test this toolkit all the way from, as Alex said, what we can define as a simple user case of understanding the source and treatment of an infection under these conditions, all the way through to advanced cell therapies and regenerative medicine for crew who are too far from conventional medical intervention to be able to be helped that way. So a lot of reliance, a lot of automation, a lot of independence necessitated by these missions will be delivered medically and in research through our toolkit. We have a short break now for Q&A. The next few slides after this will be from ESA talking about the strategic deployment plan, which is actually a really interesting topic, how we plan to develop this over ESA's objectives through 2040. But right now, because we've all been talking for quite a while, and really this is a community consultation and should be interactive, we'd like to open this to the floor for Q&A. We have, these are all question one, because they're all equally prioritized, I suppose. But these are really just to guide our thinking. These are questions that we'd like to know the answer to from the FDT perspective and from an ESA perspective as we take this forward. But we really want to know what are the unknown unknowns? What have we missed that you can help advise us on? So I'll pause now and open the floor up to questions if we have a roving mic.
Hi, my name is Insa Schröder from the GSI in Darmstadt. My question is, you have this huge toolkit, let's say it. You perform a lot of different things within this toolkit. How do you certify that it is not, that you don't have contaminations everywhere? And I mean only even contaminations, one cell type to the other, one astronaut's IPS to the other, whatever else.
That is a great question, and a tricky one to begin with. So yeah, obviously contamination for this multi-use facility, sterility and decontamination is going to be really important. So standard methods of sterilization, so UV, I suppose, is probably the most common one to make sure that we don't have any live biological material being carried over to the other situations. But also I think it's important to note that particularly for For the really critical missions, the long duration missions to Mars, we'll have likely 4 crew members, so we'll only have 4 different genotypes. If a lot of these experiments are going to be performed with crew relevance in mind, it's likely that most of the experimental samples will be from one of those 4 crew members. So we only have to really consider 4 different genotypes, 4 different patient samples, obviously different cell samples and different levels of potential contamination from microbial contamination in the environment. So there is a lot to think about in terms of how we manage that sterility. So, great question.
Yeah, thank you. I wondered whether there was any strategic decision by ESA to just focus the experimental lab just on cell culture and 3D culture, because I think you may be really missing a trick there. With the best will in the world, cell culture is, or in vitro work, is limited, maybe not least for in terms of maturity of cells and what it will allow to be tested and so on. Is there any reason why there are no animals, for example, in the system?
For ethical reasons, we are still not performing experiments with animals in flight. Other agencies perform, but ESA still is not addressing that. Okay. Or cannot.
Or maybe thoughts around other ways of that preclinical step?
What, sorry?
Any thoughts around the step from cell culture to human?
Well, we have developed this tool to really allow discovery, research, to develop research on health, and also to support health monitoring and diagnostics. So I think that we will use this tool for as much research that we can perform, even addressing those steps and addressing those technologies that may be needed. The tool, how it looks now, it may be modified further to address further needs, to address further transitions that are needed. This is, for now, a concept of something that we want to achieve when we reach to Mars. And it's actually good questions that you bring, because maybe even having those notes will help us defining it further, adding to it further. But it's a good question. But one of the goals is really also performing the necessary research. Maybe my colleagues also want to add something to that.
So I think an integrated system would be really useful, maybe nematode or something like that. Sorry, an integrated system, so a fully integrated system like a nematode. C. elegans.
Mm-hmm.
Yeah, I agree. I know there's a lot that's missing in this toolkit, and a lot of it has been done for targeted efficiency reasons, to make sure, if we wanted to, initially the plan was to incorporate microbiology into this, because infection is one of the things that we're really interested in space, but it was really hard to conceptually understand how we could incorporate microbiology understanding, stool samples, for example, into this system without the risk of it being extensively contaminated. And I think, there's a lot of xenogenic issues if you start incorporating, murine cells or, living mice in space, or even nematodes, the risk of contamination. That could potentially be another facility, or particularly since this is more of an applied medical scenario rather than a basic research scenario. Maybe that isn't covered under Bioculture Toolkit, but yeah, I take the point, Anne, it's well made.
Good morning. My name is Yelena Kozlova. I work in Uppsala University in Sweden. We had already some attempt to send stem cells to space, and they've been with Axiom 3, with Marcus 1. And we see that the stem cells feel great in space, better than in ground control. They proliferate faster, and they have more potential for differentiation. I actually have a presentation, but I didn't have invitation to present it. But if somebody interested, I will be happy to show some slides. But my question is, in relation to your talk, is are you planning to collect fibroblasts from astronauts before they go to space and prepare iPSCs and perhaps some simplified pre-differentiated stem cells which might go together and use this facility to keep there?
Yeah, very interesting.
Yeah, I mean, a quick answer, yes. I mean, so I think that a plan that we thought of would be useful was, since we have the ability to upload a lot of material, we can take a variety of crew samples, iPSCs, and pre-differentiate them or even keep them as pluripotent stem cells, and then upload those as a whole bank of patient-specific cryovials to begin with. But yeah, certainly it would be really interesting to look at what that iPSC potential of astronaut fibroblasts during a mission or post-mission could actually be. So, interesting.
And I want to clarify. Hello? Oh, okay, sorry. I want to clarify. So here today we are not discussing about the specific science we will perform. We are talking about a tool that will allow us to make science according to the needs that we will have. So there will be bottom-up science, top-down science, so focused exploration science. So we will definitely address what the science community needs and what ESA needs to perform space exploration. And of course, we welcome topics, but the focus of today, it's really to give a tool that allow to perform that science, that kind of science. We want to do that if it becomes relevant for the scientific community or if it becomes relevant for ESA. But what I want to emphasize here is that we need a lab, and a lab in space. We need a mini hospital as well. So, and this is what we are trying to pass on, so that you or other scientists can perform the science that you need, and so that we can protect crew health for situations where they will not have a doctor, they will not have the needed components to treat their situation. So that's what I want to highlight.
Sami.
I just wanted to ask a question about, I know obviously this is very high concept, but you may or may not have quite a lot of dangerous materials within this bioculture facility, which may necessitate 3 layers of containment. So if you are taking out and installing modules for decon, how are you, like, just the liquid interface itself is very challenging from an engineering perspective. So how are you going to address that, or have you thought about how you're going to address that? Because I think that's going to be a massive problem going forward.
Yes, but that's a massive problem for everything that we do. So we are not the developers here. So, of course, you know, one of the things that I will explain a bit later briefly is that this is a concept. The work that will entail will not, to be optimistic, maybe 20 years, maybe more. Because we need to address that. One thing is developing something for Earth, which is already rather complex if the thing is complex. But if you go to space, it's like... So we will definitely have to address that. We will not fly something that will not have the correct level of containment, and we will not upload something that is unfeasible. But we will have to address problems. That's why I say, maybe at the end of this exercise, when we start designing it for real and go through phase A, phase B, etc., it will look completely different. Maybe we will realize that we need two closets, one for this, one for that, because it can just simply not go together, something like that. But the concept is there because we need that. We will need that. So.
I just think this concept of having this very integrated system, you do need to take things away, and I think that's going to be one of your greatest challenges in this whole toolkit concept, is especially if you have dangerous materials up there, just being able to mate 2 systems together while not breaching those layers of containment is going to be quite difficult.
Yeah, and that's why I say maybe when we reach the point that we actually have to come up with a design that works, it might just simply look different than what we were hoping for, and maybe we will need more crew operations that we were expecting, but we need something feasible that provides the capabilities, because we will not have them. The same support we have on LEO, they will not happen if we go to Mars. So if we want to go to Mars, we have to have this. Otherwise, we may have problems and the crew might not return healthy, or we may not be able to do research. So why going to Mars if you cannot do that? But yes, I really acknowledge your comment. I think, again, please don't think that we are kind of dreaming. We are not. We know that once we start doing, or if this is just a concept, we don't know if we will be able to develop it in the near future, how we will collaborate, etc. But we know that there will be challenges. The thing is that if you would say someone, I don't know, 50 years, like 100 years ago, that you would have a space station like ISS on Leo, everyone would call you crazy. You were not crazy, it happened. So it's how we need to approach things. It will happen for sure. And technology will evolve, so.
Yep.
If I may, maybe it's a great question, and maybe it's the right opportunity to be able to develop new standards, which are not yet being developed.
Yeah, good points. Yeah, I think just to follow up on that, automation. So, a lot of potentially dangerous procedures in biopharma are now performed by automated liquid handling to remove humans from those environments. So, adding, one of the rationales for the increased level of automation is not just efficiency, but it's also increased safety for crew. I think we've got another few slides to present on strategic deployment, and then we've got another Q&A at the end, if that's okay. Do you want to do another question?
It's fine. No, it's fine. I thought there were some questions over there.
Should we do one more question, and then we'll move on to the last slides on strategic deployment, but there is another Q&A at the end. Sorry.
Yeah.
Sorry, Judith Buchem from the LMU in Munich. I wonder if you have a clear concept of your AI capabilities, because you mentioned this. I mean, it's integral. We know we need it. And there are several functions one could imagine, such as assistance for procedures, assistance for readout, integration of data, and then even diagnose things. Also human-machine interface. Speaking from my own experience, I know it can take 10 years to come to a certain point of or level of functionality. And if we think of 20 years in the future, do you have a clear concept? Do you want to use 1, 2, 3, 4 AIs? What's the hierarchy?
Great question. Inash? Yeah, we don't know.
Thank you, Judith.
Yeah, so as I said, we do have another Q&A at the end to finish the session, so please keep your questions until then. We just wanted to finish with a couple of slides. Inash, do you want to present these? We've talked about it a little bit already, but just to summarize and formalize what ESA's destination plan and strategic development plan is with regards to this toolkit.
Okay. So as I highlighted before, we are bringing the idea on the table. We are just bringing the idea because no one is still thinking about it. And usually when you start thinking about it, then it takes years, but then you need to do it faster. So we are just, because we are now in a new approach, as you have seen in the other presentations from ESA, we are now thinking about Moon and Mars. We are already thinking preliminary what we will need if we reach Mars and what we can do on the way to Mars, what we can do now that can already contribute to developing this idea, to make it happen, to make it progress. As I said to the other lady, it might look completely different when we reach there, but at least we are putting the idea on the table that it needs to be developed. So basically, we know it's demanding. It will not take 1 year. It will not take 5, not in the next decade. And I would say we are optimistic if we think that we will be there on 20 years. It might be, but it's a huge thing, and we recognize. But we can start now with few small things, few small activities to already address these needs. We will definitely need a phased development. So we will not build everything, connect everything, and fly it. No, it will not be like that. It needs to have one model at a time, tested, demonstrated, etc. And then, of course, we don't have all the expertise. We don't have all the necessary resources to develop it. We don't even have... We have interests, but we have to think about the overall roadmap on space exploration from all our international partners, from industry, from the science community. So we don't want to do it alone. We don't want, and we should not. So we need to collaborate and we need to think about how together we can bring up the best technologies for this tool. And then, of course, let's not start from scratch. It's already complex enough. So, like whatever it's existing already, let's take that. There is a lot on Earth that exists. We can simply try to address those existing technologies and advance them to reach a higher level of technology readiness. So, it's to address all these challenges, we really have to have this approach. Otherwise, it's impossible. And how we could do it would be, again, this is a vision, it's a vision, just really to show you that we can already start now using the collaborations and the objectives today to start. So we could use, for example, Leo for building the first modules, the most interesting or needed ones for Leo to give to test functionality, to test integration, some small integration between 2 modules, 3 modules. We could already start there, addressing the questions of level of containment as well. We can start small. You have heard a lot of words here today: imaging, AI, integration, automation, cell culture, code storage, preparation. It's a lot. So 1 or 2 instruments, or 1 or 2 with modules. So let's start small, and let's start with preliminary science, discovery science, or exploration focused science, using those first preliminary development. And then as we move to the moon, we start having those challenges on communication delays. We start maybe having crew availability. It will be much less because the crew will be extremely busy in the initial lunar missions. So we need to integrate a bit of automation, or automation and having more autonomous tool with few modules again, and perform some research again. And then once we reach Mars, that will come in many years from now, it will not also be tomorrow, maybe it will not be in the next 30 years, but we want then to really have something that is ready to support the complexity of the Mars mission, that is really ready to support the problems of communications, the problems of resupply, the problems of the needs for in-orbit analysis and recycling, and really to provide the crew a life support system that they can rely on should they get sick, should they have a problem, should they have an emergency. Because at the end of the day, we want the mission to be successful, we want the crew to be healthy, and we want to support the crew with the operations and activities they have to do. And then use that complete tool to really give to perform advanced research. So it's ambitious if we think on a short timeline. It's not ambitious if we think on a long one. It will be just the natural evolution of what we will need when we reach to Mars. And we are starting now. We are just putting the idea on the table because we have to start sometime. And this is the way to start. So I wanted to finish with a sentence from Peter Drucker. The best way to predict the future is to create it, and we have to start now to create it. Okay, and now questions and answers again.
Thanks, Anash. Any more questions from? Conceptually, it's about 2.5 meters on the CAD model, but that is just an artist's impression.
We are not, again, it's just we are not the developers, we don't know. It's just a concept.
Just one question from industry-wise. When do you want to start the real development?
The only thing that ESA engaged in now is really to define the requirements and the concept. So we know there is a need. Actually, when this started, it started as a bioculture facility. But as we discussed, the concept evolved, and we said, no, we have to address other problems. Otherwise, it's just a single thing we have to address. So what we just simply engaged was to define the requirements. Now, having the green light to deploy it, we are not there. Like we just defined it. We will present it, we will share it, we will discuss with other partners, and if there is an interest from other partners, from delegations in ESA, because also we are an European agency, so we have to have that interest. If there is an interest already, then of course we will start small, but we will start, but that we are not there yet, and that's why I always highlight, we are just presenting the concept. Some questions about can we do this kind of experiment, or how is the size? We still did not design it. We are just saying, look, we need to start thinking about this. And if you want to start thinking about this, by the way, for sure, at least these instruments, these modules you will need. And it would be nice to have an overall thing together. It might be that it's not possible to be together because of, I don't know, design feasibility, but at least we need to start thinking about it now.
But if I may add, the major element of it, it's also that it's expandable and versatile, and this may fit really to this approach to go step by step, and to really you can start with a small.
It's modular.
Small module, and then expand it.
So it's modules. You put them together, and it will be exactly. So.
If you go from a modular point of view.
Yeah. We forgot, actually, I think we forgot to use that word, but it has been very, very told, you know, during our discussions, always modular. Also because we want to add more things. It may be useful to add, like James mentioned, we might add a 3D bioprinter. A 3D bioprinter will be a different thing, but if we can connect them, like it's modular, so I know it adds complexity, but again, that's the concept that we are thinking of to start with.
Yeah, and just to add to that as well, I think one of the essential elements, particularly from industry, is this element of interconnectivity, universality, interoperability. Particularly in Europe, we're very good at establishing standards. What's the standard way of transferring samples between modules that can be developed for 20 years, that doesn't have to be redeveloped, and then whole elements of the system have to be redeveloped. So, if there's, I think, one of few key take-homes from this is that that's what we want. We want modules that can interface with each other. Industry is going to be essential in developing what those standards are.
I just have a comment on, so far our lab work is we consume and we throw away, which of course is not what we want to do. So is there any work already ongoing in terms of how can we recycle media? How can we recycle whatever material that we're consuming? From somebody who's running a lab right now, that sounds a bit like science fiction.
You mean it sounds like science fiction that we say that it's possible to recycle?
For me right now,
yeah, it's ambitious, but it's essential. So there was a really great talk yesterday from Zhao, who works in cultivated meats. So I've also done some work in cell agriculture, cultivated meat, where, in the body, your blood doesn't pass through once and then go. It's recirculated. It's scrubbed of waste, replenished with extra nutrients, and that's kind of the thinking that we need for making cellular agriculture and cultivated meat more efficient, and also for platforms like this, also for all of our work. Disposing of such huge amounts of cytokine growth factor-rich culture media after a single passage is excessive. So I think there's a big drive for developing that technology for a variety of applications for closed life cycle, closed loop cell manufacturing on Earth. And I think there's a big drive and a big need for it in terms of efficiency and sustainability for bioscience research.
Well, also one thing that we have to add is that it's, again, we are including recycling to the proportion that is possible. Of course, there will be waste still. There will be things we have to upload and we have to pay for the upmass. Maybe not, but again, if we don't invest on research and on technology development to address those needs, we'll never get there. And maybe in 20 years from now, 15 years from now, it will not look science fiction anymore because it's done on Earth. Because science teams will be able to recycle and not to waste. I'm not an expert, but that's what moves technology. So.
Nobody is an expert at the moment, but there is a lot of active work being done on those exact same things. So particularly in terms of the filtration, how you get rid of nitrogenous waste and lactate, and then you can recycle your media, which is 99% good. So yeah, a lot of work already being done.
Dieter Blottner from Charité Berlin. So I think it's wonderful to have this kind of brainstorming because, I mean, science fiction is one thing, but on the other hand, I fully understand that we should bring laboratory medicine to space because the priority is the crew health. But I was wondering, your module looks very, very great, but what about the fundamental science? To me, it seems the more we get from Luna to Mars, the less we can do fundamental science and must go back to clinic, to a mini hospital. And the more we get in automation, yeah, this is absolutely clear. But I mean, fundamental science does not need always automation because things are even more complex. So I would say the first priority, sure, is crew health. And the more we go into space, the fundamental science becomes secondary priority, or is this wrong? This concept.
It is.
So please keep in mind that we need this also.
Yep.
We can just agree with you. I mean, around the table there were exactly these discussions, and you may see it's still a space research, a medical kit, so it starts with research. But I think I also learned from this meeting already. I mean, we talked about boredom and so on. I think they need to be engaged and to do research and to do fundamental research and hands-on research. And as James pointed out, there will be a glove box probably. So this maybe it will save time when you have the other things automated to concentrate on your research that you may need really to evolve with your own hands. But we believe, I mean, this is it has not shifted during the discussion in itself, but it was very clear that these two elements, these two pillars, play a big role. And we are, in that way, quite happy also with the ESA approach that we have identified as space enabling and space enabled. So this is, along those roads, I think we should continue, and I agree with you. Science should not be forgotten, especially.
No, and it will not. It will definitely not, because we want to push for both streams, and if we can facilitate that, we will facilitate. We have the tool has to be there to protect the crew, but the tool is there also to exactly allow us to do the mission. And what is the mission for? Is to reach Mars, but also to do science. It's to and they will have a lot of time if they go to Mars. They really will have a lot of time. So.
Also, I believe that whilst the tool has been presented also from a medical point of view for addressing emergencies and these sort of things that come up the first time, I mean, hopefully it's not going to be just one journey, one travel. So fundamental science will be very important to be able to predict what will happen all the following times.
Yeah, there's, you can just automate the boring bits, like imaging. I hate imaging. It would be the biggest driver of boredom in the crew, I think, if they have to do imaging.
Hi, this is Maura Strigini from Saint-Etienne. How do you see the complexity of these projects compared to, say, a big telescope or rover? And how do you envisage about collaboration with other agencies?
Well, I do not develop telescopes, so I cannot comment on that. Nor I have someone here that is working on the science department and developing satellites. So I do not know the complexity. I'm not a developer. Not that I wouldn't like to, but I don't know the complexity. But it's complex, and it's a good comment, because it just shows that if we are able to fly this technology to space, like telescopes and big missions, scientific missions, then maybe this should also be possible, and maybe it will be as costly, but it's also possible. In terms of collaboration, as I said before, we still did not assign for the development. So it's not yet like, oh no, we will develop and let's start this. It's a concept. And we will start slowly bringing this concept to the ESA delegations, and also to other international partners, agencies, science community, industry, etc., to really see if there is an interest to support us with this. And if there is an interest, we will start small. We start with first modules and instruments that are really necessary anyway already, and that if we go to the moon, maybe it would be nice, I don't know, to have a culture facility and imaging. And then the crew, of course, we don't have the other, so the crew has to take the sample from the cold storage, maybe prepare it, But then culture and then imaging, maybe we can start with it and go. It's something that is already needed. So, and then when you do that, you start attracting more people. So it's a growing scenario. So yeah, we just have to share the word and start small. Start small, because if we start small, we can achieve great things, I would say. So.
Just wanted to ask you, because Mars we considering like in 20 years time, and in 20 years artificial intelligence will be very well developed, and are you considering that first trips for preparation for humans will be by robots when they will prepare, and then humans' trip will be not so challenging? What would be necessary to go to Mars at first? What cannot do robot? Does ESA has this concept?
I think that the reason why we want to go to Mars is also we want to bring humans to Mars. It's different. It doesn't need to be humans. We have ExoMars. So we are already sending them. We are already planning to launch ExoMars, and it's a robotic capability. So that will happen. But we want to ExoMars or Rosalind Franklin. But we want to bring humans. So we are already bringing missions to Mars, but we also want to bring humans. Is an ideal. It's an ambition. The same way, for the same reason, Apollo missions happened. It's like. We have just to, it's just something we want.
Joe?
Yeah, so I arrived a bit last minute, so I don't know if you've discussed this already, but coming back to the media recycling question. So I guess the amount of media that we use in these experiments is quite small. So I don't know if the nutrients that are in the media are worth recovering or not, but what about the water? Because media is mainly water. Do we know if the media can be somehow included in the water recycling units that we have nowadays?
Yeah, I think that's a prime driver, in terms of upload mass or, unnecessary extra upload mass, it's water. Culture media, as you say, is 99% water. There's no reason why we can't recover that. And there's obviously a lot of systems for recovering astronaut water and recycling into drinking water with very high fidelity, high purity. We're actually starting to think, so in my lab at the moment, we've got a project seeing if we can develop recycling methods for media that we can reuse in media, and making sure there are no contaminants like that could impact cell cultures. So yeah, so it's very interesting. It's a critical element to make this sustainable, that huge amount of water mass that we use for bioprocessing for cell culture and for analytics too, which is going to be harder to reclaim. Any more questions? If not, then everyone can get to the coffee machines early. Thanks very much for your attention and for your contributions. This has been extremely useful, so I think on behalf of the team, I'd like to thank you very much for your participation. Thanks.
Thank you.